Hi guys, welcome back to my channel, and today we're going to work on the AP Calculus BC exam, and we're going to jump into the worked examples on Unit 1, Limits and Continuity. So without further ado, let's get started right into it. Okay, so first one, so this part is part A, and the use of a calculator is not permitted on this part of the test, so we should keep that in mind. Okay, so the first question is, I'm going to paste the equation here. Okay, let's put it here. Okay. The quality is pretty bad. Okay, it's not that bad. Okay, so it is asking you to find the limit of this function when the value of x is getting closer to 0. So how can we do this? So let's just so for this example, you can just basically use the substitute method. So see, cos x is equal to 0 minus 5 multiplied by cos 0, and we obtain an answer of minus 5. So this is how you work on this example. Okay, so the next question, if b is different from 0, then evaluate this limits. I'm going to put it here. Okay. So just remember that. So as you can see that this is getting, so if you use a substitute method, you will get 0 over 0. So it is undefined. So how can we do this? So let's see, let's look at these numbers. What can you see? Okay, you see that you can easily notice that 2 multiplied with 3 would be 6, right? So we can rewrite the equation like this. Oh, I'm sorry, the function. Makes sense, right? Yes. Okay, and you can see that this will be the function will turn into a defined equation. Okay, and it's going to equal to, which is going to substitute b in here. So it's going to be plus b triple and equal to, this is what we got. So yeah, those are the first two examples that we have worked on. It's pretty easy, right? You can see that it's definitely not that hard at all. Okay, so I've pasted the next 3 questions here, so that we would not have to switch the app that frequently. Okay, so let's look at example 3. So I can see a square root here. So I'm going to think about conjugate multiplying. So we're going to do that. So I'm going to alter the function a little bit. Here you go. I'm going to multiply both the numerator and the denominator with this. Just like that. Okay, so I'll obtain this. Okay. This is pretty weird. Okay, we have 4 minus 4 equals 0, right? And x with... Oh, I can just... Wait a minute. Just keep it like this. Let's just write it like this. But it will be easier. So the function will become this. Looks very simple and is not undefined anymore, right? And now I can just substitute 0 for x or 0, sorry. And it's going to equal to 1/4. Okay, this is the answer. Oof, it's not a clean way to put it, but that's the idea. Okay, let's move on to the next example. I guess I'm going to temporarily delete this. The next example. Okay, so this one here, you might see that if we substitute, we can get something like this. And I'm afraid that it's undefined, so we've got to have another way to solve this problem. And how about this? I'm going to rewrite the function like this. As you can see that oops, a mistake. When x is increasing and not going to stop, then we're going to have this and this being closer to 0. Therefore, the limit of this function will be minus 6 over 2 equals to minus 3, and this is what we're going to get. Okay, that's for now. Oh wait, did I just delete? Oh no, my 5th example. Okay, I'm going to paste it again. Hold up. Okay, here we go. So this is our 5th example. I'm going to move it down here. So we can use a similar method to work on this example, right? So we're going to divide it. Let's look at these numbers, okay? So you might now thinking about, should I divide both the numerator and denominator by x squared or x cubed? The answer is x cubed. Always look for the largest number, okay? So I'm going to rewrite this. Remember, notice this minus symbol, okay? Because it's going to affect, in some cases, it's going to affect our answer. So I'm going to rewrite the function like this. As you can see, I'm dividing everything with respect to x cubed, and I obtain this. And as you can see, this one is getting closer to 0. This one is also getting closer to 0. This one also getting close to 0, and this one is 2. So our answer is going to be 0/1, which is equal to 0. So the limit of this is equal to 0. It's easy, right? It's not that hard. Okay, let's move on to the next example. You gotta be careful. So, as you see now, the degree of the numerator is larger than the degree of the denominator. In this case, the degree of the denominator is larger, so we obtain a limit of 0. But in this case, it'll be different. So I'm going to divide both the numerator and the denominator with respect to x squared, just like how I did with the above. Okay, just like this, and we obtain 3/5/x plus 8/x squared. And you can see this is getting closer to 0, this is getting closer to 0. So our whole denominator is getting closer to 0. So we will obtain the result of 3/0, which is this. You can see the pattern now. For this example, the degree of the denominator is larger, so the value is reaching 0. And in this case, it's the opposite. So the value is reaching this. Okay, the value is going to be like this. See, they are like the opposite. And sometimes you can just guess the limit based on the function's characteristic, just like that. Okay, so let's work on the next example. Example number 7. Ooh. I need to close some tabs. Okay, just like that. And I'm going to paste our function right here. I'm sorry if this look a little bit messy. X is decreasing. And so for this, it's really important that you take a look. You should be cautious and take a look at this minus symbol. Okay, so just like the above, we're going to divide it with respect to x, right? Because this one we have like a square root and x squared inside of it, so it's going to be like that. But you gotta remember that this square root symbol is always represents the positive value, right? It's always positive. So here we're going to be cautious. So in this case, we're going to rewrite the function like this. Oh, my brush is a little bit large, right? I'm going to increase it. I'm going to separate it into two parts, just like that. And as you can see, here is when the minus symbol matter, because in this equation, remember that x is smaller than 0, right? So the square root of x squared is going to be minus x instead of x. I've seen some students who wrote it like this, and this is also wrong, and this is wrong, right? Don't write it like that. It's wrong. So we're going to write it like this. Oof. It's equal to 3x over minus x and the rest of the function. Okay, here you can see that this is reaching 0, okay? So, and this is going to be like that. And yeah, so we can conclude that the limit of this function is going to be 3 over minus 1 multiplied with square root of 1 minus 0, and it's going to be minus 3, right? It's minus 3. So yeah, this is when you have to pay much attention to the minus symbol here, because it will affect your answer. We gotta be cautious, guys. We need to be cautious. Okay, so let's move to the next example. Wait, just let me delete all these layers. Okay, so next we're going to have this example. Example number 8. If fx is like this, find the limit when x reaches the value of 1. So for this, so we need to remember this. So we have one-sided limits, right? And we also have this. So okay, so here's like a visual way to think about it. So I have, this is our value for x, and this is 1. And on this side, which when x is actually smaller than 1, we're going, which is 1. From this side, we're going to write it as x reaches 1 and with a little minus symbol on top. And when x reaches from this side, which means x is larger than 1, we're going to write a symbol like this, and the limit when x reaches 1 only exists when we have these two guys equal to each other, right? And in this case, it will exist. However, if they not equal, then it does not exist. Okay, so let's take a look at the example. We're going to find out whether the limit of fx exists or not. So let's see. So I'm going to calculate. Oops, did I just erase the question itself? Okay, so we're going to take a look at it. So now I'm going to calculate the limit when x reaches 1, but on the left side. Okay, and here, because we have like x is smaller than 1, so we're going to have to take a look at this first equation. So it's going to be like this. The function is like this, and in this case we can just substitute x for 1 and we will obtain this is equal to e. Okay, and now I'm going to calculate the limit from the other side, and you can see here now x is larger than 1, so we've got to use this function. Okay, it's be x squared multiplied with e, and I'm going to substitute 1 for this. There we go, 1 squared and e, and I'm going to obtain e. So as you can notice that the limit from both sides are equal, right? They're equal, which is a good thing because it proves that the limit when x reaches 1 exists and it's equal to e. So this is conclusive, right? Yay. But if it's not equal, then it's also not a bad thing. It just means that the limit does not exist, and trust me, it happens all the time. So this is our 8th example, and now we're going to move on the next one. Oops. Okay. So we have the limit like this. So as you can see that if we just basically use this substitute method, we're going to obtain like this, which is undefined. So we're going to have to find a way to solve this problem. Okay, so what should we do? We can see that in this case, let's take a look at the numerator and the denominator, right? So let's take a look at the denominator. We've got e is power to x, right? And as you can see that this one, the rate of increase is quite large. Actually, we're going to notice the rate of increase of these guys, right? Because it is increasing exponentially, right? Because the x is here, not like in there. And we're going to take a look at x powered of 3, and what do you see here? It's increasing at a much slower rate, right? So this one, the rate of increase for e power to x is much larger than that of x is power to 3. So we can see that when x approaches infinity, the value here is increasing much more than the value here. It's going to be a little bit something like this, right? So we can conclude that. And remember that this expression right here indicates that the denominator is smaller than 0, right? So we can conclude that the limit of this function will actually be minus infinity. This one is pretty tricky since you've got to take a look at the rate of increase and then compare it between the numerator and the denominator. But once you get the hang of it, it's going to be much easier. Okay. Actually, what I meant is that the rate of... Okay, no, it's totally fine. Sorry. Just got a little bit mixed up between these things. Okay, so we're going to move on to our next example with the appearance of sine. Okay. So now we have to find the limit when x reaches 0 of sine 3x over sine 4x. And firstly, I need you to recall this. So it's already established that the limit when x approaches 0 of sine x over x equal 1, right? So we're going to use this to tackle this. Okay, so we're going to use that in order to solve this problem. So I'm going to rewrite the function right here to appear something similar to what I've just written. Okay, so we've got sine 3x over 3x, right? And now I'm going to put 4x here. So sine 4x. And now we got something's really wrong here. We're going to need to multiply this with 3 over 4. Okay? And now, what do we got? We got this. It's going to be closer to 1, right? This one is approaching 1. So our limit is going to be 1 multiplied with 3 over 4, and we're going to obtain 3 over 4 as our final answer. Easy, right? It's not that hard. Just like that. Okay, move on to the next question. Okay, just let me read it. So we're going to take a look at problem number 14. Oh, I'm sorry, 11. What's wrong with me? Sometimes things like that happen. Okay, so what do we see here? Let's take a look at this. We have t squared minus 9 and t minus 3. Don't you think that there's something special about it? Obviously, right? Because we have t squared minus 9 is equal to t minus 3 multiplied with t plus 3, right? And this can be crossed out if we're going to put it like that. So what I'm going to do is I'm going to multiply this with t squared, the square root of t squared minus 9 in order to, well, just deal with this annoying square root here. So I'm going to write it like this. So we're going to have 3 square minus 9. Wait, okay, so this one right here can be rewrite as this. I'm going to cross out the t minus 3, and what are left is this, and when substituting t for 3, we're going to obtain 6 over 0, which proves that the limit is infinity. Okay, let's move on to the next example. The graph of a function f. Oops, what just happened? It's shown in figure. Yeah, here is a figure, right? This is our figure. Which of the following statement is or are true? Okay, so I'm going to paste our question. So as you can see that the function is discontinuous at x equal to 4, right? This one indicates the discontinuity. So, okay, the limit when x approaches 4 from the left side equal to 5, and let's go check that. So x approaches 4 from the left side, and the limit going to see that yes, it's going to be 5, so statement 1 is true, right? So the next statement states that the limit of x when x approaches 4 equals to 2. And is this true? Because we already have like the limit from one side equal to 5. So if the limit when x approaches 4 exists, it must be 5, not 2, right? And we're going to prove it. When x approaches 4 on this side, it's going to be 5, and when x approaches 4 on this side, it's going to be 5. So the limit is actually 5, not 2. So this statement is false. X equal to 4 is not in the domain of f. So this statement is also false, because if x equal to 4 is not in the domain of f, then f4 does not exist. But it exists, and it is equal to, what is our value here? 2, right? Equal to 2. So it is in. 4 is in the domain of f. So this statement is false, right? And we only have our first statement being true. Okay, this is how you approach this problem. Phew. Okay, on to the next problem. Oh yeah, and oops. We're going to example number 13. Find the horizontal and vertical asymptotes of the graph of the function. And here, calculators are allowed. Okay. So, if you put this function into our graphing calculator, you're going to see something like this. Okay, so I'm going to open grouping, right? Desmos, my best friend. Okay, so I'm going to put this function right here. 1 over x squared, what? X squared minus, plus x minus 2 plus x minus 2. So here you can see that there are some asymptotes, right? There is like a horizontal asymptote of 0 and two vertical asymptotes at x equal to minus 2 and is it minus 2? Yes, minus 2 and 1. Okay, so now we're going to prove that that is our asymptote. So as first, for the horizontal asymptotes, we're going to find the limit of fx when x reaches infinity, right? So when x reaches infinity, it's easy, right? So the whole thing is going to be close to infinity, right? So it's equal to 0. So we have the horizontal asymptote is is y equal to 0. That's our horizontal asymptote, and it is evident when you look into the graph. Okay, how about vertical asymptotes? As you can see in the graph, there are 2 asymptotes, right? And we're going to account for both of them. Okay, so you see that. So how to find vertical asymptotes? We have to find the value of x such that the limit of x will be x1, or such that lim x, which is x1, is going to be infinity, right? And as you can see that if this equation is reaching infinity, then the denominator is reaching 0. So we're going to solve for x squared plus x minus 2 equal to 0, and we're going to obtain the value of x equal to 1 and the value of x equal to minus 2. So we get 1 fx equal to infinity, right? Wait, no, it's not that. No, it's actually depends. So we've got to take a look at our graph, right? So this is 1, and when x approaches 1 from the left side, the limit is actually minus infinity, and if x approaches 1 on the other side, then the limit is going to be positive infinity. So there are actually no limits for this equation, so it does not exist. However, we've got this equal to this. So x equal to 1 is a vertical. Asymptote, right? It's a vertical asymptote. And we're going to do the same when we substitute x for 2, right? X minus 2, I'm sorry. Okay, it's going to be, let's open our decimals. Okay, positive infinity equal to minus infinity. So x equal to minus 2, sorry, there's a minus symbol here, is also a vertical asymptote. So you can see here we have 3 asymptotes, 1 horizontal and 2 vertical. Okay, this is how you, and our graph is going to look like this. Yay. And see 2 vertical here and 1 horizontal. Ooh, scary. Okay. So that's it for question number 13, and we're going to move on to question number 14. Find the limit when x is the greatest integer of x. Oh, yes, so when x approaches 5 from the right side, like this, right? So x is larger than 5. So you can imagine that x is something like this. Something like this, right? So therefore, x inside bracket like this is going to be 5, right? So let's substitute 5 into here and 5 into here, and we're going to, and remember that x is larger than 5, so our denominator is actually smaller than 0. So it's going to be something like this. So to 10 over 0, but like this 0 is actually not 0, it's negative, right? So it's going to be minus infinity, right? Okay, let's move on to the next example. Find all x values where the function is discontinuous. Okay, so as you can see that if x is undefined, right, when this polynomial expression is equal to 0, and we're going to solve for this. You can put it in decimals like this, just like use your calculator to solve for it, and you're going to obtain x equal to minus 6 and x equal to 2. So here, another way, if you don't want to solve this polynomial equation, you can just factor it into x as 6, like x was 2, 0, yeah, and you're going to find this as well. So no matter which method you choose, you always obtain these 2 values of x that will make fx undefined, therefore discontinuous, right? So we can conclude that this function is discontinuous when x equal to minus 6 or 2. So yeah, I'm too lazy to write that out, but like you get the idea. Okay, so let's move on to the next example. 16, for what value of k is the function gx is continuous as x equal to 3. So as you can see that this function has two different expressions, which depends on which side are we considering when x approaches 3. So in order to value k to be continuous at 3, let's imagine any function you can imagine at x equal 3, right? It is continuous when the limit from both sides is equal to this, let's just say y1, equal to this value of y, yeah? So when, if you want this function to be continuous at 3, then f3 must be equal to the limit when x approaches 3 from both sides, right? So this is what it must satisfy, what k must satisfy in order to make gx, it's g, in order to make gx continuous at 3. This is what it has to satisfy. So you see that g3 is equal to, let's substitute 3 for this, and it's going to be 9 plus 5 equal 14, and it's also equal to the limit when x approaches 3 on the left side, right? On the left side of the number, right? When it approaches like this, when x is smaller than 3. Okay, and we have the limit of gx when x is approaching 3 on the other side is equal to the limit x approaches 3 when it's larger than 3 of 2x minus k, and we're going to substitute x for 3, and we're going to have 6 minus k, and we have to make it equal to 14. So k is going to be 6 minus 14, which is minus 8, and this is the value that we're looking for. K must be minus 8 in order, so we're going to conclude that this k equal to minus 8, so that gx is continuous at x equal 3. Yes, this is what we're going to have. Okay, so determine if the function fx is continuous as x equal 2, and explain why or why not. So we're going to use the same method that we had used for the last example, right? So we're going to see that the limit when x approaches 2 is going to be this, right? This expression x. So as you can see that this one is actually, if you substitute it right here, you can see that it's undefined when it looks undefined when, but we can totally factor it out, right? So this polynomial equation could be rewrite as this, and we're going to cross out x minus 2, and we're going to have left with x plus 7 is going to be 9. Okay, and f2 is actually 12. And now you can see that because 9 is not equal to 12, so the limit of fx when x approaches 2 is 9. It's not equal to 2, so the function fx is not continuous at x equal to 2. It's going to look something like the graph that we've like before earlier in the video. It's going to look as something like this. No, it's not going to look like that, I'm sorry. Yeah, something like we're going to have like something, a different value like above here, and so it's discontinuous. Yes. Okay, let's work on the next example. Oof, that's a solution. It just gave you a flash of it. So, given fx as shown in figure, find f3, lim fx, and explain why or why not. So this one is actually pretty easy. Okay, so let's take a look at the first. So you go to look for f3, and you can see that we're going to look at this black dot right here, and we're going to count. So 0, 1, 2, 3, 4. So f3 is going to be 4. So limit of fx when it approaches 3, and you can see that actually these the question B, C, and D can be solved at the same time. When look at the graph, we're going to look at the line, like the curve right here, and we're going to see that both the limit of fx when x approaches 3 on both sides is going to be 0, like the white dot over here. It's going to be 0. So it exists and it is equal to 0. So the answer for the 3 questions will be 0. Okay, and the last question is if x continuous at x equal to 3, explain why or why not. And so it's really easy to, it's not that hard to tell that it's not continuous as x equals to 3, because the limit when x approaches 3 is not equal to f3, right? We have the limit equals to 0, while the actual value of f3 is equal to 4. So it is discontinuous, and is really evident in our graph right here. A function f is continuous on this interval, and some of the values I've shown below. Okay, this we're going to need to do a little bit of drawing for this question. I'm going to put it right here. If f has only one root, r, on the closed interval, and r is not equal to 0, then a possible value of b is... Okay, first, looking at this question, you might think that why is it so confusing? But let's break it down. Okay, so a function f is continuous. Okay, so we're going to draw a little graph here. Like, I am not the best grapher, but I'm trying my best though. Something like this, right? Okay, let's extend it a little bit. So I got here with x2 minus 2 and 2, and the value of f are shown below. And we'll see, so this is a value of 3 and this is a value of 4. So we're going to have the story. Okay, so it's going to have to pass these through, right? If f has only one root, r, on the closed interval, and r is different from the 0, then the possible value of b is. So I'm going to find the value of b when x is equal to 0, when x is here. Okay, so you can see that if the function is going to be like this, I'm sorry, it's got to pass this, right? Something like this, or right, you're going to see that it will actually have two roots. It will have two roots. So remember that if b is smaller than 0, no matter which graph you might draw, there would be two roots. So it's not possible for b to be smaller than 0. If b is equal to 0, then the root is going to be 0, right? But the root is not 0. So if b equal to 0, r will be 0, so it's not possible. If b is larger than 0, something like this, right? Then it might or might not cut this axis. So it might not intersect with the L, or it might, right? And it even might cut it like this too. But at least there's still a possibility that R might have one root and it is not 0. So it's possible, but not conclusive, but it's possible, but it's like the best choice that we have right now. So D is our correct answer. Right, so that's pretty much our exam now. Okay, I'm going to see if there are any. Oh yeah, we have one problem left, and we're going to finish our session for today. It's been pretty long, maybe. Okay, let's evaluate the limit of this function. So as you can see that there's something very intriguing about this expression, because remember that sine x squared plus cosine x squared is equal to 1. So we can totally substitute sine x squared as this. Okay, and now we're going to see a part in right. We're going to divide both the numerator and denominator with 1 minus cosine x. Right, so this one's going to be 1 minus cosine x multiplied by 1 plus cosine x, right? And we're going to cross out 1 minus cosine x, and we're going to have 1 over 1 plus cosine x, right? And then we're going to substitute x for 0, right? And cosine 0 is 1. So our limit is going to be 1 over 1 plus 1 equal 1 over 2. So this is the value that we're looking for. It's easy, right? The thing is that you have to look at this sine square x and then think about the relations it might have with the numerator. So that's it for now. It's the end of our studying session. And I hope that now you got a deeper understanding of this problem. And I'm really grateful to be your tutor for today. Okay, so that's it for now, and thank you for watching this video, and remember to subscribe to this channel for more lessons like this. Okay, bye bye.